chapter 11. So chapter 11 is on ethers. Okay, and then we'll also cover epoxides and sulfides. Yeah.
Are we still going to have like recitation if we need it?
Yeah, definitely. So that's what I mean. Today, we do have a chemistry club meeting today, but I was thinking, you know, starting on Monday, we'll have them, you know, I'll stay through 12:45. And we'll do that Monday, Wednesday, you know, as needed. So yes, by all means, please stay if you have questions.
On Monday.
All right, so what's an ether? So an ether has an oxygen just like alcohols, but however, the H has been replaced by another carbon chain. So you see that, you know, this would be just like the alcohol, right, a carbon chain with an oxygen, but the H has been replaced by another carbon chain. So basically it's R, right, O in the middle, and then another R, another carbon chain. They can be the same, like this example here, okay, or they could be different. They don't have to be, you know, identical or symmetrical in order to be an ether. If they are as shown here, right, sp3 hybridized, then the angle, again, is pretty close to the ideal, which is the 109.5. Okay, so that's general structure for an ether, an oxygen bonded to two carbons. Okay, now with ethers, unlike alcohols, alcohols could not be bonded to an sp2 carbon. Remember that we talked about that because that forms an enol, and an enol tautomerizes to a keto group, to a ketone or a carbonyl group. So, but the ether does not. So you can have an sp2 hybridized carbon as part of your ether. So, for instance, this is an ethyl vinyl. So remember, vinyl is two carbons with a double bond in the middle. So you have two carbons on this side, which is the ethyl part, single bonds, and then you have the vinyl, okay, with the double bond. And for ethers, that occurs because there's no H in order for you to be able to do the tautomerism, because you have to remove that hydrogen of the alcohol. Okay, so you can have a mixture, or both sides could be sp2 hybridized. You can also have cyclic, you can have a benzene as part of the chain. There's lots of variety as to what those carbon chains can be in the ether. Okay, but the important thing is that oxygen with the two carbons. So naming, again, we've already covered this last semester, but I'll make sure every chapter will review. So for the ether, you do look for the, you know, I like to say, and here it says longest chain because that's how the book says it, but it's really not a continuous chain. Does that make sense? Because it's carbon-carbon, then oxygen, right? So it has to break it up because it is not a continuous carbon chain. So what you want to do is which side is the longest or bigger of the two. Of course, in the first example, they're the same, ethyls. So you just choose one side and you call it the alkoxy substituent. So this would be two carbons, so you would say ethoxy. And then you would make the other side the parent chain, which would be ethane, right? Two carbons as well. So ethoxyethane is the IUPAC name. Does that make sense? So in this case, what's bigger, two carbons or six? Six. Does that make sense? So you would say that the alkoxy is the smaller of the two. So that's ethoxy still, right? But then the parent chain is this cyclohexanol. Does that make sense? So you split it right where the oxygen is. The smaller becomes the alkoxy. The larger becomes the parent chain, right? And of course, there's some wedge and dash, so you do have to consider the stereochemistry here. That's why you have the 1R, 2R, right, 2-ethoxyhexanol, right? And this is carbon 1, since the alcohol is part of the parent chain, so 1, 2. That's why you have the 2-ethoxy. Does that make sense? And then on this here, so what's bigger, 1 carbon or 4? 4. Does that make sense? So this would be methoxy. Right, and then this would be 2 also, right, off of the second carbon, 2-methoxy, 2-methyl, and then you have 3 carbons, propane. Does that make sense? Right, so the longest chain is 1, 2, 3, right, 1, 2, 3, 1, 2, oh, sorry, 1, 2, 3. Does that make sense? So the longer chain is 3, but there's also this methyl here off of carbon number 2. So it's 2-methyl, 2-methoxy, 2-methyl, and then the propane. longest chain. So that's the IUPAC, but then you see in parentheses the common names, okay? And the common names are accepted by IUPAC. And what we do is we name both sides. So this would be ethyl, this would be ethyl. So there's two ethyls. We say diethyl, right? Just not to be repetitive. And then you call the oxygen ether. So diethyl ether. Does that make sense? Okay, so here, right, this one, it's just the only thing that changes is the trans, because there's really not a good common name for the cyclohexanol, so that one doesn't change. What about over here? Right, so it's methyl, and would you agree that this is T-butyl, right? Terbutyl, the carbon that is tertiary in the middle, right? So this is going to be, right, terbutyl methyl ether. Okay, so whichever one you want, it does, you know, to me, either are acceptable. Now, on AL, if it says IUPAC, then you have to do the alkoxy. Okay, they don't accept both. But on the exam, I will accept whichever one you want to do. Does that make sense? How to do the naming? Okay. Now, cyclic ethers also exist, so the oxygen is also attached to two carbons, but those two carbons are cyclized, or, you know, more than two carbons, obviously, but there's a cycle associated there. The oxygen is part of the cycle, so we call this a heterocyclic compound. And the way we name these is we take the oxy, and this is a common name, and the IUPAC also accepts these. So ox is the prefix, so you see ox is always in the front, right? Okay, and then for 3 carbons, okay, it's irane, so oxyrane. Okay, then atane, so oxetane for 4, oxolane for 5, oxane for 6, and then if you have 2 oxygens and 6, it's dioxane. Does that make sense? So unfortunately, these you just kind of have to, you know, memorize these endings. But the one we usually see is the epoxide. So this is a group of compounds which we'll talk a little bit in more detail towards the end of this chapter. Okay, but this is the one we're going to see most often. So the oxyrane ring. Okay, now you can use the ethylene oxide. So what that is this was a double bond. Would you agree? Maybe? Did you see 2 carbons with a double bond? And then you did an addition where you added an oxygen and then you cyclized. So this would have been propylene, right? Butylene. So you could also name it based on what double bonded compound that came from. So that's another way. I don't know that it's any easier. but again, mostly we'll see the oxyrane. So that's the one you want to kind of star that you'll probably see again. Okay, otherwise, the others, you just have to memorize. There's not a lot of rhyme or reason for those suffixes there. So those are the cyclic ethers. All right, so after naming physical properties, so even though these compounds are polar, right, you can imagine that you would have a charge difference because O is more electronegative than C. Okay, so you do have, right, a pocket of negative there over the oxygen and then in making the carbon more positive. However, there is no hydrogen, right? So there is an interaction which we call a dipole-dipole interaction. Okay, that's one of the van der Waals forces. Okay, but there is no hydrogen bonding, so very weak, right? Dipole-dipole interaction. Okay, so what that means is because you cannot hydrogen bond like you could with an alcohol, you now have a much lower, right? The boiling points and melting points will be much lower. So the Y is because you cannot hydrogen bond. So they're going to have melting and boiling points closer to the alkanes. Okay, remember the alkanes have very low boiling and melting points.
What's the answer to the Y again?
The Y is because the alcohols can hydrogen bond, but the ethers cannot. So hydrogen bonding is the Y there. Now ethers are hydrogen bond acceptors. The oxygen right, is going to have that partial negative charge. So let's say you were in water, right? Water would have the hydrogen to interact with the oxygen and make a hydrogen bond. So solubility of ethers, right, that's going to still be able to dissolve in water as long as they're small. Okay, because the oxygen can still, right, accept the hydrogen. But it cannot hydrogen bond with itself. It can only form these dipole-dipole weak interactions. Does that make sense? So the hydrogen bonding is not there. Okay, so that's the Y up there. Okay. So how do we make ethers then? Okay, so the way to make ethers is called William ether synthesis. So that's the most common method. This is an SN2 reaction, so it's a SN2 displacement, and you are displacing, basically you're substituting the I, right, the halogen here, or X, so it could be a Cl, a Br, or an I, okay, and then you are adding, right, the nucleophile, which is your alkoxide, right, came from the alcohol, so remember that you form this when you react an alcohol with a sodium metal. So we did this reaction last time. Okay, you form those sodium alkoxide ions. So you would do that. And so the reaction would be here, right? The I leaves, and then you have the product. Does that make sense? Right? And again, this is an SN2 mechanism. So this is going to happen all at the same time. Does that make sense? And remember, this is a methyl, right? It's not going to be able to undergo an SN1. Okay, and then of course you get the sodium iodide, right, as an ion. Does that make sense? How you make an ether? So this is the most common way. It's called a William ether synthesis. Now there's a bit of an issue here. If you recall, this is a base, right? So these kinds of bases tend to lead to a elimination reaction rather than a substitution reaction. So that can be an issue. And the issue is really on how much yield you'll get. So if you have a competing reaction, what's going to happen to your yield? It's going to be lower. Does that make sense? And in organic chemistry, we really want to make our product with the highest yield possible. That's really our goal. Okay, so in order to get the highest yield, we want to use methyl or primary halides. That's going to improve our chances of getting the reaction to go SN2 rather than elimination. Okay, so in this case, right, this is a methyl halide. Would you agree? It's a methyl group next to a halogen, right? So this is going to lead you to the SN2 product, which is the ether. So what's the problem here? Is this a methyl or primary halide? It's a carbon next to a bromine, right? So that's a halide. This is right? This is a tertiary. That's not going to undergo SN2 at all, right? So this is a problem, right, to get the ether. So the product is actually an elimination product. Does that make sense? So to me, these look really similar because this is methyl and this is methyl. Would you agree?
Yes.
But do you understand that this is the halide and this is the oxide?
Yes.
Yeah.
Right? I need the halide to be methyl.
Yes.
So it doesn't help me that the oxide, the alkoxide, is methyl on that second reaction, right? Does that make sense? So I have to look, this is the halide in this reaction, and it is tertiary. That's not going to help my yield. See, look, tertiaries fail to do substitution. You get the elimination product only. Does that make sense? Now what about secondary? So what if this was a secondary halide? Okay, you have a lower yield. You still do the substitution, but the elimination is going to lower your yields for that. Okay, and again, why, right? Because you have a competing mechanism. So you don't make just one product. Does that make sense? So there's a requirement basically for this reaction, and it is what? Primary or methyl halide, right? That's what you're looking for. If it's a tertiary halide, will you have the ether synthesis? No. You'll have elimination only, right? And what about the secondary? How many products are you going to have to draw for that? 2, right? The ether and the alkene, right? The elimination product. Does that make sense? So you're not going to be able to have 100% yield, of course, right? It's going to be more like 60-40 or something like that. Does that make sense for ether? This is for the William ether synthesis. There's other ways of making ethers, but this is the most common way. Okay. So these are the halides in green, and then the alkoxides are in purple. So you have to make sure the small one, right, is the halide. So this is a problem down here.
What's the blue? Or these are the purple is the
Purple is the alkoxide. Basically the nucleophile, right? This is going to attack the carbon with the halide, and the halide is going to be your leaving group. So these 2 are your nucleophiles in purple. Right? And then the leaving group is your halide, your bromines. Yeah, the ion, basically that came from the alcohol. That's called an alkoxide.
A little faint. We need to get new markers for the chemistry teachers. We should get you neon colors.
Neon
so
colors,
you can write
that would
neon.
make it a little bit more
Yeah.
impact, high impact. So that's again the ether synthesis, but there's an alternative method to making ethers. Okay, and that's an acid catalyzed reaction. And again, when we talked about acid catalyzed reactions with alcohols, it was a dehydration reaction. So what would we anticipate the product of a dehydration would be? Water plus, what would the organic look like? Double bond, right? It would be an elimination reaction as well. Okay, so that's what we expect. Okay, but there is a way of churning that mechanism and making ethers. Okay, and so the way to do that, it has to be a primary alcohol. Okay, so the OH has to be at the first carbon. That's the first requirement. The second requirement is that you have a low temperature. Usually these dehydration reactions occur at 180 or higher. Okay, we are lowering the temperature to 140.
Is it uniform 140? Always has to be 100?
Yes, it's 140 if you want to form the ether with this method. So because of the acid, remember, you're going to protonate the alcohol and make that oxonium ion, right? So that your leaving group is water, right? Remember, we have to always do that in order to make, right, the leaving group a better one. So we have the acid in order to do that, okay? And then you need, of course, to have at least 2. So this has to be an excess because you're basically combining one of this with another, right? That's how you get the 2 carbons on the other side, right? It came from another one of these. And then you're getting rid of water. Does this make sense? All right, so if you had, and then you had another one, because there's 2 of them, right? You would get rid of the OH of one and the H of the other. That's how you would get your water molecule. Does that make sense? And then you would connect the O to the C, right, to make your ether. Right? So CH3, CH2O, CH2, CH3, right, which is the product. So you're combining two of your alcohol molecules together.
So when you're doing this reaction, just out of curiosity,
Sure.
when you go to separate the water and the diethyl ether, how would you do that?
It's fine because diethyl ether is not very soluble in water. It's too big. So they actually will separate. We use diethyl ether in the lab later on this semester to do a separation reaction. So that's considered an organic solvent. Okay. So this is an alternative. And diethyl ether, again, is a very common solvent. We use it all the time. So it's made in large quantities in the industry. So this is the industrial method that is used. So when you're trying to scale up and make a lot of it. So, but again, that temperature is really important, right? And you have to have primary small alcohols in order for this to work. Okay, primary, right? The carbon that the OH is attached to is primary. Does not work for other. Does that make sense? So these are the requirements for this alternative method, which is really a dehydration reaction, but at lower temperature. And this is the mechanism for it. Again, we have to protonate, right, our alcohol group, the hydroxyl. Okay, we use the sulfuric acid to do that. Now we have our oxonium ion, which is going to leave, right, as water. Okay, and that allows our other alcohol to attack as a nucleophile. Okay, and so now we just have one more step, right? We have to deprotonate, because that's not part of the ether there, right? A new oxonium ion. So we use a water molecule, which is made as part of the mechanism to remove the hydrogen. And then it regenerates your acid from the first step, right? Remember an acid catalyst? The catalyst has to be regenerated and made back. It doesn't get used up in the reaction. Remember, that's part of the catalyst definition of a catalyst. Does that make sense? So that's the alternative process there. Now we can do an acid catalyzed addition reaction. So not dehydration, but an acid catalyzed addition reaction. And now you're going to use a stable carbon. So you are going to have to form a carbocation. So it's going to have to be tertiary, right? Secondary or tertiary. So this mechanism won't work for small ones, right? Does that make sense? So the carbocation, which is going to come from your alkene, has to be stable. So tertiary, right? Secondary will work, but it will not work for primary and methyl. Now the combination is then with a small alcohol, a methyl or a primary alcohol. So methanol or a small alcohol. Okay, so that's what's, the best combination. And then again, you add a catalyst, acid catalyst to it. What's that acid catalyst going to do? Right? Promote again the protonation part of the mechanism. Okay, and then you will basically, right, add the OCH3 to the carbocation. Okay, so let's take a look at that. So this is for an alkene, a tertiary, right, alkene with a small alcohol. So that is the ideal conditions. Right, so you've seen three ways of making ethers, right? The first works better for primary, right, methyl, right? Okay, the second, it has to be a small primary, right? And now you see a way of making it if you have a tertiary. Does that make sense? So, I mean, I gave you three reactions for a reason. Because each of them, right, is going to allow us to really react any kind of, right, make any kind of ether, if you can think about it that way. Does that make sense? So I promise I don't just give you all these reactions for no reason, right? And I gave you a substitution reaction, an elimination reaction, and an addition reaction. So there are all three mechanisms being used here of our 5, right? And we're doing acid-base also in that first step. So again, we need to protonate, right? So make that oxonium ion, and in this case, it's going to allow us to open the double bond by picking up the hydrogen. So it makes a carbocation, and then the carbocation gets attacked by our alcohol. And again, there's an extra hydrogen here, right? There's still an ion, that oxonium ion. So we do have to take care of that. Okay, and that's the third step. So again, now we're not doing this in water, so we have another methanol molecule comes in and picks up the hydrogen, and now you have your ether. Does that make sense? So again, right, so to summarize, I gave you, right, the three reactions, because they each, right, are gonna focus or be useful for one of the types, right, certain type of carbon that you're starting with. So you
So
want
if you
to
asked
keep that.
us just random question of what kind of reaction would you use to make an ether, you can see if it's primary, tertiary.
So you would have to look at what kind of carbon were you
the small
given.
alcohol.
So if you were given a primary or methyl, you would say a William ether synthesis, right? If you were given a tertiary, then you would say you would use the acid catalyzed addition. Does that make sense?
Yeah.
So you have, there's a reason, there's a method to my madness.
There
And in
always
chemistry,
is.
gotta work with my ego. So that's how you make ethers. So now if we have an ether, what can we do with it? So one of the things that we can do is cleavage. So we can break the ether bond. Okay, and so we do this in order to make alcohols. Okay, so we can take an ether, react it with, okay, an acid halide, right? So HCl, HBr, HI, so HX shown here. And if you have 1 mole, then you have 1X, right? So you're going to be able to break that bond and make RX, right? And then the RO is going to combine with the H to make your alcohol. So you get 1 alcohol and 1 halide. If you have 1 mole of HX, right? 1 mole of this. So what are the requirements here? Okay, you do need a strong acid, which is also a good nucleophile. So that's why the HX is really the, the acid that we use here. And it does work better for HI. So you see you get about 57% yield, and you get 48% for HBr, and it's even lower for HCl. So
That's why it's the weaker nucleophile. Is that why it's the weaker nucleophile?
correct. So I is a better nucleophile, right? Br is the next best, and then Cl is lower. And we don't usually see fluoride as a nucleophile. So you can see the HCl down here. So that's the cleavage. Now, what if you had 2 moles? So if you had 2 of your HX, so in this case it's 2 HBr, well then you could see it that you would get, right, the first cleavage would give you 1, right, RX, the Br would be there. And then the second one, the Br is going to be a good nucleophile, so it's going to attack the alcohol, get rid of the OH as water. Does that make sense? And make a second halide. So you don't get an alcohol at all. You get a water instead. Okay, so if you have 2 moles, you don't make an alcohol at all. You just make 2 halides, and then the water that comes from the substitution of the OH, right? So these are substitution reactions, right? With 1 mole, you're substituting what? The X is substituting for one of these R's, right? That makes sense? And here you have 2 moles, so you're going to do the substitution twice.
Jimmy?
Right?
Can you explain that?
Come again?
Yeah.
Yeah, so with
Just the
one
play-by-play.
mole, right, you're just gonna do one substitution, because you only have one nucleophile. 1 mole, right, means 1 X. So that 1 X is gonna do one substitution, right?
Got it.
But if you have 2 X's, right, 2 nucleophiles, you're gonna do it once, and then you're gonna have an alcohol, so you're gonna do it again, right, so twice.
Water.
Because you can get rid of the water from the alcohol. And that's a reaction we did last chapter. We used HX with alcohols. So that's the difference. You get 2 of the halides. So this is the mechanism here. So of course again, right, we got to protonate our oxygen because we got to make it, right, have something to leave. So we protonate, and you have your oxonium ion. So then the nucleophile comes in, attacks the carbon, and then you have the leaving group, which has the oxonium ion attached. So that's how you make your alcohol. And then the Br, right, came in from the nucleophilic attack. That makes sense? So it was a substitution, and it is SN2, right? The attack and the leaving group, that happens at the same time. So this is a substitution reaction. But remember that if you had a second, right, another mole of your Br, then your alcohol would start up here again, right? It would get protonated, you make the oxonium ion, the Br attacks, and then you get another one of these in water, which is the leaving group. Does that make sense? So if you have a second mole, right, then the reaction is going to happen again.
What if you have more moles?
If you have more moles, well, then it depends on how much of the alcohol, or I'm sorry, the starting
So
ether
it'll
you
keep going
have.
until it goes to water.
Yes, you'll keep going till it's all reactive. But what's the limiting reagent here?
Halide.
Right, so you really want to keep that at 2 moles. But if you had more, then it would react, you know, as much as you have. But in this case, we're using the halide as our limiting reagent. 1 mole versus 2 moles. Does that make sense? So the cleavage of an ether. So we can make an alcohol that way plus a halide with 1 mole, or 2 halides with 2 moles. Okay. Now what about tertiary? So those were primary, right, or secondary. But what about tertiary, allylic or benzylic? So we consider these to be very stable, right, carbocations. So they're going to be particularly sensitive. Okay, because when you cleave, you can leave, right, the carbocation, and now that is going to be very stable. So these are particularly very reactive, so you don't even need heat or anything like that. So it's a very quick reaction. So you can see that this is going to happen with HCl, for instance, at room temperature. So these are, what kind of mechanism? SN. It's tertiary. This mechanism that's here, not the one that was on the previous. This one, tertiary, is SN1.
Because there's 2 strings.
So these were, the one over here, this is SN2. But for tertiary, it's going to undergo an SN1 mechanism, and the SN1 mechanism is very effective, right? You literally don't even need to heat it up. Right, and remember that HI was, you know, required, right? Better HCl will do, right? Remember, HCl only gave you 38% yield. It's going to give you a much higher yield here, tertiary. Does that make sense? So HCl.
Because it's weaker.
So HCl is a weaker nucleophile, but it doesn't matter what's driving this reaction, right? Remember, this is SN1, so the carbocation stability is going to be determining, right? That's the rate limiting step. So the nucleophile is not part of the rate limiting step, so it doesn't matter the strength of the nucleophile.
But HCl works better. But you were saying HCl works better than...
Either one is going to work about the same. But with the other mechanism, the SN2, this HCl is not as good as HBr, which is not as good as HI. So it matters what the nucleophile strength is. Here it doesn't matter. So this could be HCl, it could also be HBr, it could also be HI, and you would get similar yields.
Because instantly more.
HF is not a good nucleophile, it's considered a poor nucleophile, so we usually don't see substitution reactions with the fluoride ion in general, so.
But if it was an S2 reaction, then that's when
Then the HI is, again, the Cl won't be as good a nucleophile, and that matters, so you get a lower
we
yield.
have HI, HBr,
And then HCl, in that order.
And you want to get soda.
Yeah.
I'll add on the soda.
So that's the cleavage of a tertiary. Okay, and then the last reaction we'll talk about today is oxidation reaction. So remember, oxidation is a gain of oxygen, and the ether already has an oxygen. Would you agree? Here. Okay, so it's kind of a a unusual product that we get that's specific to ether oxidation. And notice that the oxidation is in the presence of O2. So we are talking about right here, right in the room. So we have oxygen. So this will happen just by standing, right, an open container in the room. You don't really need to add an oxidizing agent like chromic acid or permanganate or anything like that. So this will happen with just the oxygen, O2 gas, okay, from the air. And what you get is what we call these hydroperoxides. So you see the OOH. Okay, that's a hydroperoxide, and that is considered an explosive. So when we have a bottle of ether in the lab, for instance, okay, once we open it, we have 1 year to use it. If we don't use it within a year, we actually have to dispose of it properly.
Explode it.
Okay, and even when we open it, and let's say we're going to use it a couple of months later, we have little sticks that test for the hydroperoxides to make sure that it's safe.
And it doesn't explode.
Yes, because if you put that in a vial and heat it up and you have the explosive component, it will blow up the glassware. So
What
how long
causes
does
it
that
to just?
spontaneous reaction occur?
Yeah.
that's what I mean. I mean, usually, a year is a safe bet. We don't see the hydroperoxides within that time. If you maintain the bottle, you open it when you need it, put it, close it when you don't. We put it in the refrigerator. So you take certain precautions to make it last longer. But if you pour, some ether and you kind of leave it, out, well, ether are volatile, so they're going to evaporate if you leave it open. But, if you weren't taking as many precautions and oxygen got in there, it could be less time than that. But a year is a safe bet, and it has we have that time frame to use it. So, and this reaction occurs by radical mechanism. So remember that peroxides are good as starters for radical reactions, and so basically that's what ends up happening. The O2 gets converted, right? This looks like a peroxide, right? It's just a hydroperoxide because it has a hydrogen here. And it happens with all types of ethers. So you can see diethyl ether, or the diisopropyl ether.
The one works for ice.
It's an issue for all ethers.
So how explosive is it? How explosive?
Like I said, if you heat it up, it's not going to explode the bottle all by itself, sitting there. But if you heat it up, because it's volatile, then it'll blow up like the vessel it's in. So if you have it like in a round bottom flask, the glass round bottom flask, it'll blow up the flask. So we were doing ethers. So remember that an ether is an oxygen bonded to 2 carbons. Okay. So in today's lecture, we're going to see the O attached to 2 carbons. It's still an ether. However, it is cyclic. So we call it an epoxide when we have 3 members of that ring. So it's 2 carbons, right? And then the oxygen in between those carbons causes it to cyclize. So this is called an oxyring, if you remember that common name, but I think the easier name is epoxide, and I believe that OWL likes to use that instead of oxyring, but either name would be fine if you saw it on an exam, but this is the cyclic ether, okay? And then this is oxyrain or the epoxide. Then you can have, right, if you add some carbons to those two the two that are part of the cyclic, then you're actually talking about, right, dimethyl in this case. So you would add those as substituent names and then keep the oxyrain. Does that make sense? So this would be, right, the two carbons and then two substituents here. So why 2, 3? Why not 1, 2?
Because it's still a carbon chain.
It's still a carbon chain, very good, right? So it's actually 1, 2, 3, 4, right? So look at the common name, it's from butene. So, but if you use the oxyrain, then you can use the ring and then have the dimethyls, but you still have to consider that you have a continuous carbon chain. Does that make sense? So this one, would you agree that the epoxy is here, right? But the largest chain is actually going to be your cyclo, right? Your cyclohexane. So that is a little bit different. So cyclohexane is the parent name, but then the epoxy is the substituent name if you have an epoxide ring. So, and then it would be 1, 2, because the main chain is the cyclo, and you're always going to try to give the lowest number to the substituent. So hopefully it makes sense that this would be 1, 2, right? And then if you had any other substituents on the ring. Does that make sense? So the naming. All right. So these are the epoxides, so cyclic ethers, and we're only going to focus on the 3-membered ring. There's 4 and 5 and 6. We saw those in the naming portion of this chapter at the beginning of the notes, but we're going to focus on the 3-membered ring. So how do we make these epoxides? So preparation, right? So these often come from the ethenes, propenes, butenes, so from the double bond. Okay, so an alkene is added to oxygen, that's one preparation, in the presence of a catalyst, right? So in this case it's silver, so it's a metal catalyst there. And then what happens is you open the double bond and you make the bond to the oxygen. Now why do you get 2? Because you have 2 oxygens, right? So there's a potential of making 2 of these epoxides. Now this is again just to make the oxyrain, so it only works for the ethene, fails for all other alkenes. So if you want to make a substituted epoxide, you have to use a different method. Yeah? No, just rubbing your hair.
Yes, just from
All right, and this is called air oxidation, so O2. Okay, so this is air. But this is probably the more common method, and it uses a peroxycarboxylic acid. So we know that a carboxylic acid is COOH, so it's a carbon, 2 oxygens, and a hydrogen. The peroxycarboxylic acid has 3 oxygens. It's COOH, or CO3H for short, okay? So in the presence of this peroxycarboxylic acid, and these are just some examples of them, so MCPBA, this is how I will write it down, so you kind of want to be familiar with some of these abbreviations, but basically it's metachloroperoxybenzoic acid. So again, right, the benzoic acid would be this part, right, but you're adding an extra oxygen, okay, and then the chloro here is meta to the carboxy there. Does that make sense? And then this is MMPP. So this is an ion, but again, right, you can see the 3 oxygen there, right? So also comes from a cyclic, and this is from phthalate. And then this is peroxyacetic acid. So that's the simplest one, and this is the one usually I will give you, or like you said, this one here, which is all the letter soup there. But just keep in mind, it's that 3 oxygen, so there's an additional oxygen to the carboxylic acid. And what you do is you couple that to an alkene. And now you can do a variety of different alkenes. It doesn't have to be just the ethene. So this is really a more, common way of making these epoxides, the substituted epoxides. So this is the alkene plus your peroxycarboxylic acid gives you, the epoxide wherever the double bond is. Does that make sense? So wherever the double bond is, that's where you're going to have the reaction. Nothing happens to the other carbons. Does that make sense? So CO3H.
Ours is different on.
The slides are different?
It's just like,
It's probably,
Yeah. We get the carboxylic acid at the end.
but basically it's the same thing.
It's the
like
same
it's
thing.
the-
oh, I have a different reaction. Yeah, I might have simplified over just to kind of keep it really, simple, but
But it's
again, you see where the double bond is, right? And that should be where your epoxide comes in. Sorry about that. I have a note to update all of my,
We're just beginning
No,
big
it's
class,
this,
so it's
thank you for pointing it out. Then I'll go to my office and I'll put a little tag on that page. But this reaction is called epoxidation. And epoxidation is stereospecific. So what that means is that when you have a double bond, an alkene, you can have either cis or trans, right? If that's possible. So whatever the starting alkene is, right? Whatever the stereoisomer comes in. So the example given here is trans 2-butene. You make the trans product. Does that make sense? If you start with the cis, which is not shown, you get the cis. So you retain whatever the stereochemistry is of the original alkene. Does that make sense? So this reaction is stereospecific. So if you're given the product, the stereochemistry of the starting material, you should retain that same stereochemistry in the product. Does that make sense? So it's stereospecific. And it should say that on your reaction sheet. So hopefully, it'll be a reminder for you. So, all right, so what does that then indicate is happening during this reaction mechanism? So if I'm retaining this stereochemistry, it means there's never an opportunity for the carbons to rotate, for the carbon chain to be free of the double bond. Does that make sense? So if I opened the double bond and had single bonds with a carbocation, it would mean it would allow for rotation, because single bonds can rotate much easier than double bonds. So what this is saying is there is no free rotation, which means then I do not have a carbocation, which indicates what kind of mechanism? Right? Concerted. So the attack, right, to open that double bond has to all happen at the same time. Does that make sense? So I don't know if that red is on your slides or not, but you can, basically, this is indicating a concerted mechanism, because it gives you a specific, place where this attack has to happen, and there is no free rotation of the bond. That's why you maintain the same stereochemistry. So this is what we think the mechanism is like. So here's your double bond, right, your alkene, and then here's your peroxycarboxylic acid, so COOO, right, H. Does that make sense? So this is a concerted mechanism. The double bond does, the pi bond starts everything. Remember, that's the driving force opening that pi bond to add the oxygen. So one is here. Does that make sense? I think I have the numbers here too. So this would be 1. Does that make sense? So what would be next? I forgot my clicker. So what would happen next? So if I bond to this oxygen, now this oxygen has 3 bonds, right? So one of these bonds has to go. Which one goes? This one, right? Does that make sense? You open this bond to then make a double bond. So how many bonds does that carbon have now? Does that make sense? So if this is now, right, a double bond, it has 1, 2, 3, 4, 5, right? So again, a bond has to break. So which bond should I break, right? Remember, the pi bonds are much easier to break than a sigma bond, so the pi bond will break. Does that make sense? So that would be 3, right? And then of course there's that H here of the, right, carboxylic acid. So the extra, right, pair, because once I move these over, that's going to be 2 lone pairs, so this is actually extra. We'll pick up the hydrogen, right? But again, now hydrogen has 2 bonds, right? So it's going to want to break one of those. Does that make sense? What's happening? So 4 is picking up that hydrogen, but then hydrogen, that's too many bonds for it. So it's going to have to break that bond, right? And then finally, 6 down here at the bottom. So it's a pretty complex concerted mechanism, would you agree? But this is the proposed system. If it has to happen all at the same time, right, that's what the product is indicating, then it would have to happen in this way. Okay, but it makes sense again, you're making the first bond here, right? And then your last bond, right, closes the epoxide ring. And of course, this is the oxygen that is being transferred. Does that make sense? The others, right, stay with the product, right, the side product. Does that make sense? Yeah. Concerted mechanism. And again, if you follow all the arrows, it should make sense why you're breaking the bonds you're breaking in order to make sure, right, atoms don't have more bonds than they, would normally have. Carbon has 4, oxygen has 2, hydrogen just 1, right? So you have to make sure that, those things are being accounted for, okay? And so there's no room for rotation. The bond has to be right here, right? Which keeps then, right, whatever orientation the starting material is in to start with. So that's the mechanism for the synthesis there, which is also known again as epoxidation, which the carboxylic acid is going to be a main part there. Another mechanism that can be employed is the halohydrin reaction. So if the halohydrin reaction, which we did last semester for the alkenes, so remember that that's the halogen with water, so halo, and then hydrogen is for water. What happens is you transfer both, you add both a halogen, in this case chlorine, and you transfer the hydroxyl of the water. So you get a halohydrin as a product. So if you take the halohydrin and add a base in water, so sodium hydroxide here, okay, it will form the epoxide. Okay, so you can take, again, any alkene, right, a double bond, do the halohydrin reaction, and then whatever your product is, you can add a base, and it will make your epoxide. And so this forms also as a concerted, okay, but it's what we call an internal SN2, because SN2 is concerted, as you know, but the nucleophile is already part of the molecule. It's not coming from an outside source. So that O, right, the OH, right, you have to deprotonate, you form the ion that attacks the carbon and the leaving group leaves. So it's an internal SN2 reaction. Does that make sense? So this is, again, an alternative mechanism to forming the epoxides. So you want to look for, either one, as Al gives you something like this, you just want to look for the ones that might potentially lead to a product that is the epoxide. Does that make sense? Okay, this is also regioselective and stereoselective. So again, here, if you have a cis, right, starting out, okay, it shows you that you're going to get the cis as the product. So why would that be? So accounting for what you see here, why would the cis predominate? What's
Because the oxygen is so negative, or
well, and the oxygen and the chlorine, right? They have to come from anti positions because they are, right, both negative, both electronegative, carrying a lot of electrons. So you are going to have the attack always be anti. So it's going to give you that selectivity. So that's also the Regis selectivity there. Okay, so 3 ways, right? So again, the first one, that air oxidation only works for the ethene, the 2 carbons, to make the epoxide. If you want the epoxide to have some substituents or a starting material other than the ethene, then you can use either the epoxidation with the peroxycarboxylic acid reagent or the halohydrin. Okay, and then keep in mind that the halohydrin is followed by a base, right? Because the halohydrin product is not an epoxide. It has to be the reaction of the base that's going to form that.
can you go over the halohydrin part again, please?
So the halohydrin, again, this is a reaction we did last semester, and it's adding both a halogen and a hydroxyl, because you have both the X2, right, in this case is chlorine, and you have water. So you're going to add the Cl to one of the carbons of the double bond, and you're going to add the OH to the other carbon. Okay, so now what you have is, if you add a base, it's going to deprotonate. That hydrogen is going to leave. So the oxygen is going to be in the ion form, right, which is a great nucleophile. So it is going to then attack the carbon that has the good leaving group. So what ended up happening is, by doing a halohydrin, you have both a nucleophile and a leaving group on neighboring carbons. So it's an internal reaction. Does that make sense? And when you do it internally, you form a cyclic product, because there's already one bond to the oxygen, and you're going to form the second bond when you do the SN2 reaction. Does that make sense? But you have to have that base in order to form, right, your good nucleophile here. So that's why the halohydrin has to be followed by a base in order to form the epoxide. Does that make sense? These are the synthesis reactions, and just keep in mind, you start with trans, you get trans. You start with cis, you get cis. So you want to have that. If it asks for stereochemistry, be aware of that. Okay. So now what can we do with these epoxide rings? So now that we have seen how we make them, what do we do with them? Well, they are the starting material to lots of different reactions. So unlike a regular linear ether, okay, they are very reactive. So why would an ether in general not be a good candidate for reactions? Right, so why is what is the leaving group is really what you think about. So when you have an ether,
It's in between.
right, what's the leaving group? If you had to have a leaving group here. Right, remember that the nucleophile would attack here, right? And then this would have to leave. But that's not really a good leaving group. Have you seen this group in the list of leaving groups?
No.
Right? So the leaving group is not very good. So what makes the ring version of the ether a good choice? Right? So again, the nucleophile is going to come in for an attack, right? So why would this be good? Remember that cyclopropane, there's a lot of what? The angle is 60, right? It wants to be 109, 0.5, right?
So it wants to form that double bond.
Right? The angle strain is very high. Especially with the oxygen. Remember that the oxygen, right, changes that even more because it's electronegative. It wants the electrons anyways, if it can have them, right? So you have really two things here, right? The angle strain is so high that a cyclopropane, so just carbons, right, high energy when you open that up, get back to the ideal angle. Does that make sense? So there's high angle strain, and you have an oxygen in the epoxide ring, so the oxygen is going to want those electrons, right? It's highly electronegative, so there's really a very big driving force to do this. Does that make sense? To open the ring. So what is the leaving group in the epoxide but that oxygen, right? It's going to take the electrons with it, right? Does that make sense? So the angle strain is gone because it is now linear. Again, it's a tetrahedral. And the oxygen gets the electrons, win-win. Does that make sense? And what did you just make but a new bond with the nucleophile? So you can add a lot of variety by using an epoxide as a starting material. Does that make sense? So why the epoxide? Why, right? Ethers won't be reactive, but epoxides will, right? Does that make sense? Now, where's the attack going to be, right? So I attacked already, you know, because I know a little something about it. Okay, you're going to usually, right, want to attack where you have the, so the OH is going to want to go in the more substituted carbon. So you're going to attack from the bottom, so that's the first thing, it's an anti-attack. And then you want to do it, these are symmetrical. So it's not really showing you here, and the one I drew is symmetrical, but let's say there was a carbon over here, right? The OH should go where there are more carbons already.
So
Why?
it's going to go in.
Because this is like an SN2, right? So the SN2 gets hindered if you have a bunch of things. That's called beta hindrance, right? So the attack should be on the side that has the least amount of things, right? So there's no blocking the attack. Does that make sense? So that puts the OH where there is more, so we call that, right, that's the same thing as the Markovnikov's rule for other reactions that we've discussed with the
So it's
the
still
bonds.
attack that left side, you're saying?
It's just going to attack from the bottom here at this side because this side is bulkier than over here. There's only hydrogens. I'm assuming there's only hydrogens over on this side. Right, the attack from the bottom comes from, again, you don't want to do it from here. Why? Because the oxygen is what? Negative. Negative and negative are going to repulse, right? So I'm always going to attack from the bottom, so it's going to be anti, and it's going to follow Mark's rule. Does that make sense? So, and again, that thing should be on your reaction sheets. Okay, so what kind of products can I get? All right, so if I take water, and this is acid catalyzed again, right? Remember that it helps if you can make an oxonium ion, right? Add a hydrogen to the oxygen, then there's even more reason to break that bond. Okay, so usually these reactions have an acid catalyst, but basically it's water that's your nucleophile, right? So water is going to attack, right? And so would you agree that you're going to get an OH from the ring opening? And you get an OH from the water that's attacking. So you really form a diol or a glycol since these carbons are right next to each other. Does that make sense? So two OH groups. So that's when the reaction is with water, so acid catalyzed, right? Water here being the nucleophile. So again, a proton transfer to start out, right? Makes the oxonium ion, which again is an even more, right, more of a reason to open that bond up. Okay, and then the nucleophile is water coming in and attacking, right? It opens the epoxide ring. Okay, and then of course you do have an extra hydrogen, but you'll have additional waters that can come in and deprotonate so that you have, right, the alcohols as your product. So again, a diol, two OH groups in your product. Does that make sense? So that's acid catalyzed. Okay, so I already touched on this. So this reaction is always anti-stereoselectivity. So why? Right? Again, the attack is going to want to be away from where the OH is, because the OH is negative. The nucleophile is coming in negative, so there will be a repulsion. So you're going to want to attack from the other face, right, which is called an anti-attack. Okay? This is similar, if you remember, to the bromonium ion that we discussed. So whenever you have those reactions that form the bromonium, you don't attack from where the bromine is, right? You attack from the anti-face. So we've already seen something like this. Okay? And so this is an example here. You're going to attack from where? Right? The bottom, right? Away from, or you can do it from the top, away from the oxygen. So that's why you get two products, but they're both trans. Does that make sense? When you have an anti-attack, one thing is going to be going down, the other is going to be going up. So anti means a trans product, right? But you can have two possible trans, right? The trans that attacks bottom here makes this the top, right? Or if you attack from here, right? Top, bottom. Does that make sense? So, but anti means you get the trans product. So racemic mixture. Is this making sense? We've seen all of this with, like I said, the bromonium reactions, so the halogenation reactions. Now, is it impossible to make the cis if that's what I want? Right? This is the trans, if you follow the epoxide, right? The way we just talked about. You get the trans with the anti. But remember from chapter 6 also, when we did the alkene reactions, there was a diol formation reaction with OSO4, and the product for that is the CHEM, the cis. So, you know, if the desired product is cis, you can just use a different reagent. Remember that there's reasons why you get multiple reagents and mechanisms if you want to get different things as products. So the ones we're talking about today, right, with the peroxycarboxylic acid, right, followed by the acid catalyzed reaction, is going to give you trans only. But if you wanted the cis, we already actually did this one in chapter 6, the OSO4 reaction. So be mindful of what you see as a product, right? And then you can consider, okay, which way should I go? Which reagent should I use? Does that make sense? So you can make the cis. There are two methods that we learned. There might even be other methods, but these two are known mechanisms. So what else can I do with these epoxides? Well, sometimes I just want to open the epoxide and make an alcohol. I don't want to add any new bond, right? Because if I add a nucleophile, I'm going to have a different, right, functional group there. Okay, but I can actually open it with the hydride as the nucleophile. So if I use lithium aluminum tetrahydride, there's a bunch of hydrogens here, and they act like H-, and that's really uncommon. There's only a few reagents that can produce that. But the hydride, okay, as an anion, is a nucleophile, a very strong nucleophile. And what it's going to do is, again, attack, right? Open the ring. And so what you end up with is the OH, which comes from the ring opening, but just an additional hydrogen in the carbon that got the attack. So you get an alcohol, not a diol, not a new nucleophile, just hydrogen. Bless you. Okay, so you can do this type of reaction if you use, again, lithium aluminum tetrahydride. And this is considered a reduction reaction because you're adding hydrogen. And lithium aluminum tetrahydride is a common reduction agent, reducing agent, excuse me. So no additional functional groups, so if you don't see anything being added, don't let that confuse you. Think of that hydride is a possibility with the proper reagent. Okay, but like I said, the epoxide is really at the center of a variety of reactions. So we just looked at a few today, like the glycol formation with the acid catalyzed, okay, adding the water as your nucleophile. Okay, but you can do a number of different reactions. You can add, okay, for instance here, we're adding carbons, right? What's this? Cyanide, right, or nitrile is another word for that. Okay, so you get the beta hydroxynitrile, right? Remember, alpha carbon next to it would be beta, so that's why you get these beta products. You can also add another carbon chain if you do what? Which one is this one? We did this chapter 7 last time, right? This is an alkyne ion. Remember that if you add the sodium, right, to NaNH2 to a terminal alkyne, you can form that ion, and that ion is a strong nucleophile as well. Okay, so those are just adding carbons, which is difficult, but this is really, I mean, this shows you the extent. So you can make new carbon-carbon bonds, which is 1 and A. You can also do nitrile reduction, so you can add the carbons that way. So 2 is giving you that. You can form nitrogen containing nucleophiles if you use that, so you can see 4 and 3. And then heterocycles, right? So you can form cyclic if you do an internal type of reaction, so 5 and 7. Okay, and then there's even sulfur if you use the, or sorry, chlorines, right? If you use the thionyl chloride that we saw previously as a reagent. Okay, so is there a pattern to all of these, though? It's highlighted for you. Can you see it? So when I have an epoxide, what am I essentially adding? Carbon, carbon, oxygen, right? Would you agree that the highlighted portion is carbon, carbon, oxygen, carbon, carbon, oxygen, carbon, carbon, oxygen, carbon, carbon, oxygen, carbon, carbon, oxygen twice, right? Again, right? Carbon, carbon, oxygen, internally, right? Twice as well, but then connecting them together. Right? So here, it was carbon, carbon, oxygen, but with the thionyl chloride, you just substituted. But there's still that pattern of carbon, carbon, the nucleophile. Does that make sense? Can you see the pattern? Remember logic, right? We want to apply logic, learning our patterns. So anytime you have an epoxide, you add what?
Carbon.
2 carbons. Carbon, carbon, and then the oxygen. Does that make sense? Okay, so
What are we adding it to?
Well, you're adding a nucleophile to it, but I'm saying whenever the nucleophile attacks the ring, you always get a product with the same pattern. The pattern is to be observed in the product. Does that make sense? So whenever you see a product, you should be able to identify a pattern. So let me show you this slide here. This might help. So if I look at something like procaine, so you might have heard of lidocaine, it's a similar compound, so it's an anesthetic, right, local anesthetic. So if I look at this molecule, can you see the pattern? It's a big old molecule, right? But if you look closely, you should see that there's a carbon-carbon-oxygen pattern. So what you say to yourself is, if this pattern is in my product, I must have started out with an epoxide. Does that make sense? As a starting material. Does that make sense? Because I don't know any other way of adding 2 carbons and oxygen. Does that make sense? And this is what we call retrosynthesis. It's a very useful tool in organic chemistry. So a lot of times what we do as organic chemists is come up with a product we want to make. So, you know, you study some enzyme, you look at the substrate, you're trying to form, right, an inhibitor to that enzyme to cure a disease. Have you heard of this as a tool of making new medicinal agents, right? So you look at that and you say, you know what would be a great product? This. Right? You come up with the structure first. You don't know how to make it. Does that make sense? You just come up with, this is what I would like to make, right? So if in this structure I can come up with a pattern that gives me what I should start with, that's really useful, isn't it? Because epoxide is a very reactive starting material. And it's necessary, it's part of the structure of this particular, right, anesthetic. Does that make sense? So as organic chemists, we usually know the product first. We don't really know how to make that product yet. You know, we're going to figure it out. We're going to come up with a method to make that product, but we don't know it yet. So if we can identify a pattern, then it can help. And it's called retrosynthesis because I'm starting at the end, right? So I'm reversing the order of things, right? I should start with the reagents and make my product, but I look at the product first. So that's why it's called a retrosynthesis. Does that make sense? So what would I have to add to my epoxide? This, would you agree?
And the other side.
And the other side, right? Does that make sense? Which one would I add first? So how do I open my ring, right? It's a new carbon bond, right, to the carbon. So which reaction happens first? Do you understand what I mean? I'm going to have to attack away from the oxygen first, right, to open the ring. So the first reaction is this side, right? The right side. It opens the ring, right, adds this portion, which is, right, in the product. And now I have that OH, right? And then I figure out what should I add over on this side, right? It's an acyl group. We haven't done these reactions yet, but we will soon. So that's what I'm going to do on this side, right? You might not know the mechanism of all that, but you can see that I'm going to lose the water, right? Which we've been talking a lot about, right? Yeah. And then I'm going to connect this to the oxygen, right? And it is as simple as that. This is a great method, right? Easy. Okay, these reactions work very efficiently, get good yields, and I can form my anesthetic, right? Novocaine. Does that make sense? How retrosynthesis may work in organic chemistry. And this is something, again, Al likes to do. So in this chapter, okay, you'll see the last couple of problems on the EOC, they're going to give you a product and have you try to figure out, okay, how do I make that product? So look for the pattern, right? We haven't learned a lot of patterns yet. So hopefully if you can identify the epoxide pattern, that's the one we're learning with. So similar to the epoxide is the epichlorohydrin. So it's a cousin, twice removed. But basically here it is at the bottom. So this is how you make it, and don't worry, you wouldn't necessarily be asked that, but basically you're forming the epoxide, okay, but you're also having a fluorine. Another good leaving group, would you agree? Right, so the epoxide ring opening, that's a great, right, reaction. But so is attacking here and having the leaving group leave, right? So would you agree now you have 2 points where you can do nucleophilic reactions, right? I can attack the epoxide ring. Which side of the epoxide ring? Which side has less stuff?
Right.
Yeah, does that make sense? But I can also attack this carbon, right? Because that carbon has the leaving group. So I have 2 points of attack, which means even more variety. So the epichlorohydrin. Okay, so what would be the pattern in this one? So I now have carbon, carbon, right? The oxygen is going to be here, would you agree? carbon, carbon, oxygen, another carbon. 3 carbons. Oxygen where? In the middle. Does that make sense? Can you see that pattern
Yeah.
for me? Right? If I get rid of this bond, right? That's what I'm going to do when I open this ring here. Right? So it's carbon, 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 and the oxygen will be right in the middle. Carbon, carbon, right? And then carbon with an oxygen in the middle. So again, I can figure out through retrosynthesis if maybe the epichlorohydrin was my starting material. Isn't this fascinating? It's fascinating, right?
David, it's just putting down more.
Huh? Right? Yeah, so again, right? So here, looking at again, you're gonna think about what are you gonna do, right? You have 2 points, right? So you can attack with a nucleophile here, which is what's happening in the first step, right? Then you can attack the least substituted side, so you get a nucleophile on the other end. So the pattern again is carbon, 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 3, right? And the oxygen will always be in the middle because you have to attack where there's less stuff. Does that make sense?
He's lazy, he doesn't want to work for the spot.
So, well, it's just, imagine if you had a wall in front of you, right? That would be kind of hard to get to the other side.
Yeah, it's like Trump wants to go.
Yeah, it's going to get hard for people to make it to the United States, just like it's going to be hard for the nucleophile to attack. So. But that's, right, 2 spots with this epichlorohydrin, so you get a different pattern. So now how many patterns do we have? 2. Right, so if you get a retrosynthesis question, revisit this, okay, so that you can identify some patterns, and we'll continue to learn other things that we might want to use as patterns. But these again, some examples. So Nadolol, and this is a vasodilator, so it's a beta blocker. You might have heard of this as a general class of drugs that are usually given to people who have heart problems, so it helps with that. And so, balance their blood pressure and blood flow to the heart. And so again, if you look at this drug, again, it's a big old molecule that's kind of intimidating, right? So the chemist that came up with this was like, okay, this is a good candidate, but I have to figure out how do I make this, right? So if you can identify the pattern, right, again, we know that we can do these reactions using, right, one side and the other side. And again, we have to figure out which side first. With the epichlorohydrin, usually the side with the chlorine goes first, and then the epoxide ring is open, right? The chlorine, a halogen, is a better leaving group than the O of the epoxide. So, that's why the reaction is that way. But does that make sense? So again, you get, right, from attacking on this side, the left of the molecule, right? The other nucleophile, the nitrogen, attacking the least substituted epoxide ring. Does that make sense? And then you get this great drug, right? So, fascinating medicinal chemistry. Anybody want to be a medicinal chemist? But again, 2 sides. And then the last thing we're going to talk about, or actually two quick things, but so other types of ethers that might be of interest. One of them is called crown ethers. And so crown ethers, as you see here, is a cyclic molecule. And this cycle has oxygens in between the carbons. And so what happens here is there's a total ring size. So we're going to count all the atoms in the ring, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So total atoms that make up the ring, carbons and oxygens. That's the first number, 18. Okay? Then we use the word crown to identify this class of ethers. And then we put in how many oxygens we have, which is 6. Does that make sense? So 18 is the total count, everything in the ring, carbons and oxygens. Crown, and then the number of oxygens, which in this case is 6. Does that make sense? 18 crown 6. And so the molecule, if you look at the space filling, it looks like this. So what's all on the inside? Oxygens. Okay, so all of the oxygens. So what is that hole going to look like? What charge?
negative?
Yeah, look at over here, right? All that red means there's a lot of electron density right in the middle. So who would love to be in there? Something with what charge? A positive charge. And so this is really what these crown ethers are used for, is to trap these ions, these positive charged ions, cations. And based on the ring size, a certain diameter, right, is formed in the center, so you can measure that diameter, and it fits a particular ion. So the, is this the 16 one? Yeah, the 16 crown 6 that we just saw on the previous page fits perfectly potassium, K+. Now sodium is a little smaller, right, as an ion. So you can make a smaller crown ether to trap sodium. Would you say you can make a bigger one to trap a bigger ion? Does that make sense?
Yeah.
So these are a type of ether that, again, can be very useful. So the 12 crown 4 is for lithium. The 15 crown 5 is for sodium. So again, right, these are both smaller metal cations, right? And then there could be a bigger crown ether to trap bigger. Does that make sense? So this is kind of a neat use for an ether.
Really good.
So they trap. And
So these ions,
they would trap them like.
because the charges, right? So the oxygen would create this negative area. So the positive cation is going to really, bond to it based on the charge difference. So it's an ionic bond. So it eventually will release, because an ionic bond is not a permanent bond, but it allows for ions to travel and be trapped and, released when needed. So,
And we would use this as like
I mean, lots of different things like, I never say this word right, but chelating, like CHELATE, how do I spell that? So these are treatments. If you get a heavy, heavy ion poisoning, you can actually take these and then they trap the ions and then your body can release them. So that's, one use as far as like a biological application. But again, they can be used for lots of inorganic reactions and things like that as well, bioinorganic reactions.
Drano.
So, Drano.
Like, doesn't it trap all the excess stuff in the pipes to? Never mind.
Yeah, I don't know if it has a
there's
crown
probably
ether in
science
there
behind
though,
it,
but it definitely, is gonna be a way of trapping, right, excess ions. So that's one use. And then the very last thing, sorry, I forgot about these, but we talked with the alcohol about thiol. So if you substitute the oxygen with the sulfur, remember that sulfur is right below the oxygen in group 16. So you can have analogs that form. So here we're talking about ethers. So these are going to be sulfur versions, okay, which have the S, right? Instead of having an O with the 2 carbon chains, you're going to have the S, the sulfur there. And this is called a sulfide. And so, again, the IUPAC, okay, uses, right, one side, usually the smaller side, and it calls it, right, as a substituent with the sulfonyl. So the sulfonyl is the sulfur, ethyl, and then the other side is ethane. So ethyl, sulfonyl, ethane. But you can also, just like the ether, name both sides, diethyl. Would you agree? There's 2 ethyls, so diethyl. And then sulfide for the sulfur in the middle. Okay, so which side is smaller? 2 carbons or 3 carbons? 2, right? So ethyl sulfonyl, right? And this is propane, right? And the ethyl sulfonyl is coming off of the middle carbon, not the right-hand carbon, so we call it 2-ethyl sulfonyl. Right, but again, you can do ethyl, and this side is isopropyl. Remember the branch to branch? So you can actually do it that way too. Ethyl, isopropyl, and then the sulfur is sulfide. Okay? So these are thioethers. Okay, you can also have a disulfide, so two sulfurs coming together. So if you have two thiols, they get oxidized if they react together, right? So they can actually come together and form a disulfide. So again, disulfonyl, right? So we're doing the same thing, the smaller side with the sulfurs, and then the parent name, Fa. And you can also, again, diethyl, right? And then di, since you have two sulfurs. So it's really the same naming, just add the di prefix in front of the sulfide or the sulfonyl, whichever, if you want to do IUPAC or common names. And how do you make these thiol ethers? So you actually take Rx, so you can see here that you have the chlorides together, or you can have two separate Rx's and then bring them together also. But in the example, they're already part of the same molecule, so you're going to react it with the disodium sulfide, and it's an SN2 reaction. So this is going to be your nucleophile. It is going to attack leaving group, but it's going to do it twice, right? So then you end up with the thiol ether as your product plus the salt.
And it attacks it twice because of the S.
Because you're going to have an SN2 and you're going to have a nucleophile, and then another nucleophile forms, so you're going to have two attacks. If there's a strong nucleophile, it's going to do it if there's a leaving group.
Okay, because you have chloride and
Two leaving groups, yeah. And they can be on the same molecule or separate molecules. Okay, and then you can have a variation of the William ether synthesis. Remember how you have a small halogen compound, right? Attacked, and then in this case, instead of being the oxide, right, this is going to be your sulfide ion. So same principle. So that this ion is going to attack the carbon, the leaving group leaves, and you can form your thiol ether. So we did a similar reaction at the beginning of this chapter called William ether synthesis, and it has the same requirements. You must have either a methyl or a primary halide in order for these reactions to work. So it follows the same rules. So this is really an SN2 mechanism. Doesn't work for tertiaries, remember? So you can go back and see those requirements. And then what do we do? Like I said, you can oxidize the sulfides. And so when you do that, you can either form a sulfoxide, which then can lead to a sulfone. So this is a similar molecule to sulfonic acid, which, it's a good leaving group. So this is a good way of forming those reagents that you may be using. These are some mechanisms. Again, these are, not going to give you this on the exam, but it's just so you know that similar reactions can happen, right? Oxidation of alcohols, right? Oxidation of these sulfides as well. That's it.